This is Michelle Joy Arapong, and I will discuss about chromatic number. In this discussion, I will start with a motivational problem. The object on the screen, consider that one as an array of cell phone towers. Now, in order to work properly, any two towers that are close together have to be on different frequencies. So we want to ask ourselves, how can we set the frequencies of the towers so that we don't have a problem with two towers being close together having the same frequency? Well, one thing we can do is, if we have infinite resources, say we have 5 different towers and 5 different frequencies, then we could just put different frequency on each tower. But the problem is more interesting when we consider the constrained problem where we only have, for example, 3 different frequencies, orange, blue, and green. And now we have to assign them. I'll say close together, maybe 50 miles in theory, but we'll use a stick as means of measuring. So let's start with the frequency of orange. So in the second tower, okay, these guys are too close together, so let's put different frequency, okay, color blue. In the third tower, they are too close together, so it can't be blue and it can't be red. So let's put another frequency, okay, green. In the fourth tower, okay, this is too close together with green, but it could be red or blue. So let's say it is red. In the fifth tower, okay, both sides can't be red since they are close together, but it could be green or blue. So let's say this is blue. Okay, so here's one way that we could assign frequencies to the cell phone towers. Now, what did we just do with measuring with a stick? We were testing a property, the property that they're within 50 miles of one another. Whenever we have a problem like this, really we should be using a graph. So as you can see in the above screen, we're making a graph. So what we have is a case where we have our 5 towers that are arranged like this. So with our stick measuring, we realized there were edges like this. So now the question is, how can we assign colors to the vertices so that we don't have what's called a monochromatic edge? So we've colored this one red, the other is blue, and the last one is green. Now when we're doing this mathematically, it's easier if we think of assigning numbers. So red is 1, okay, and blue is 2, and green is 3. And what we want is that if any two numbers or any two vertices are connected by an edge, they have to have different numbers. But it's a lot more exciting if we think of this as coloring. So we're going to keep the analogy of coloring, and that's really what it's called. So what does it mean for a graph to be colorable? So by definition, a graph is k-colorable if vertices can be assigned values in one of the k's such that no two adjacent vertices have the same value. While putting some edges, we saw that this graph is k-colorable for k is equal to 3. That we could see that 3 was actually the minimum number of colors that I could use. So it's interesting to ask not just is a graph colorable, but what's the smallest? So let's think of an example of cycles. So Cn is generally what we call a cycle of n vertices. So we can see here, we have an example of C3, which has 3 vertices, and C4 with 4 vertices. Cn is 2 colorable if n is even. So in the even case, I can just have alternate color that's 2 colorable, green, blue, green, blue. And if it's 3 colorable, if it is an odd. If I have an odd cycle like I have here, I can do the same thing. Only the problem is I'll get stuck at one vertex. That's why I have to put another color. So the cycle we saw, the minimum number of colors that I need is 3 if it's odd or 2 if it's even. And that idea of the minimum k for which it can be k-colorable is what we call the chromatic number of a graph. So by definition, the chromatic number of chi of g of a graph is the smallest value of k such that graph is k-colorable. So let's do another example of chi of t. So where T is a tree. How would we do this? So let's take our colors away and let's just think about building a tree. So we have here a tree. Now the point is to try to use as few colors as possible. So if I can repeat, I will. So we can see that if we start at one vertex of a tree, and it doesn't matter which color you will assign, and when we look at our neighbors, we color them blue. And step down again, it's green, because by definition of a tree is a graph with no cycles. So chi of t is 2 and the chromatic number is 2. So further digest the topic, the next reporter will discuss. Thank you.